My name is Ademola Adetunji, and I'm a research associate with Meta Earth. I mostly work with the MT data, unless I have to do something else. So today I will be summarizing our recent article in Geology, where we discuss the conductivity structure associated with the orogenic gold deposit in Red Lake. I work with a bunch of people on this. Thanks to all of them. So the Uchi terrain is located in the Western Superior Province. It's bounded to the north by the North Caribou terrain and to the south by the English River terrain. It hosts multiple orogenic gold deposits, and the largest of them being around the Red Lake mine trend within the Red Lake greenstone belt. So we studied this region. I mean, it is, I judged, one of the largest Archean orogenic gold deposit in Canada, although we didn't say that here. So we investigated the region using a total of 50 broadband MT data sets. So the broadband MT means it goes from very shallow cross, I mean, not really, really shallow, to up to upper mantle, if you may. So the sites were aligned along the existing lithoprobe reflection seismic data, WS2B. And we used a couple of those sites to create 3D control for possible 3D inversion of our data set. Now, so the brief tectonic history of this region, the Uchi terrain and the North Caribou terrain, they sort of consist the record of the earlier tectonic event in the area. But what concerns us the most is the Kenorian orogeny, which occurred between 2.72 and 2.7. And during this time, there was collision between the North Caribou terrain and the terrains to the south, probably all of them together. And that ended up with the thrusting of the North Caribou, I mean, of the Winnipeg River terrain under the North Caribou terrain. So the D2 deformation happened at this time where the penetrative structures were formed. And there was also I'm sorry about that, some thing going on here. So there was also the reactivation of the earlier features. Now, the main state gold mineralization, which we all know in the Red Lake, happened during the D2 event, and it was between 2.723 and 2.712, I believe, GA. And the subsequent orogenic collapse, post-tectonic collision, D3 strain, is attributed to the late-stage gold mineralization. All the shear zones in that region must have formed during the D2 and D3 events, and the final amalgamation of the north and the south occurred later down the line around this time. So that's all I know about the tectonics. Now to the MT, I realize Eric deprived you guys of the beauty of MT, basically. So I'm going to make that up to you a little bit. So like I said, we have 50 MT sites. 5 of those were from, those ones in red, they are from the previous lithoprobe project. But the remaining 45 were acquired for us by Quantec sometime late in 2021. So we analyze this data in varieties of ways to understand what is going on, and the best tool for, obtaining the first-hand information from your MT data is using the phase tensor. So phase tensor is a non-dimensional. It doesn't contain, it's like the secret weapon. So it's uncompromised portion of our impedance. So it can tell you where you have the large-scale structures and the small-scale structures, whether your structures are 3-dimensional or 2-dimensional in nature. So in this case, we examine the varieties of options, and this shows phase tensors At depth, I mean, this at periods representing the upper crust, the mid, and the lower crust. And it's colored by the skew, which it's believed that when the value is plus or minus 3, when the value is higher than plus or minus 3, I should say, then you're looking at three-dimensional structures. Another school of thought believed that if it's 0, it's three-dimensional anyway. It's more like whatever it is three-dimensional. But then we're sticking with plus or minus 3 in this case. So, and you can see that we have a large-scale 3D structures in our data. Also, we looked at this in various ways. We colored with phi min, phi max. Everything points towards large-scale three-dimensional structure. So with that, we were emboldened to go ahead and invert our data in three-dimensional, because you may ask that the data is sort of collected in 2D, why 3D? So that's why. Now, so we modeled using 3D algorithm of mode EM, applied varieties of errors until we got to the barest minimum. And we also did a lot of resolution and sensitivity tests to ascertain that the features we have in our data actually corresponds to what we have in the model. And this is just a map of the final misfits. It's less than 2. The TIPA is a little bit over the top. The black ones are just areas without TIPA data. So with all that, we eventually came up with a final preferred model. So here are the depth slices from our preferred model. We have at 1 kilometer running through the mid-crust to the lower crust at depth at 35 kilometers. So we have a bunch of features resolved by our data. So, but mainly the resistive feature R1 and R2. R1 corresponds to the Uchi terrain and R2 to the North Caribou terrain. And by the way, this one is when you vary the resistivity a little bit, this part is less resistive than this part. This is typically greater than 50,000 ohm meters in most cases. And we have a bunch of conductivity anomalies from C0 to C4. C1, 2, and 3 are near vertical features that tends to dip from near surface all the way to lower crust, and they tend to match eventually with a C0 at the base of the crust. An important feature here and the contribution of this study is the C3. It forms east-west trending sort of feature that aligns with the Red Lake mine trend, and it demarcates the North Caribou terrain from the Uchi terrain. This is not exposed at the surface, so the actual boundary was not known. I mean, up until now, I believe they will accept. So we then pull some vertical sections along these lines to look at the resistivity variation with depth. So, and there is what we come up with, showing the large-scale structure as it extends around the area of confidence of our model. Although we use a large 3D model, but then not everywhere is constrained. So, and here is a section, this one B here, as a representative section, which shows the C2 that aligns with the lithoprobe fault, which is the Great Bear at the Great Bear deposit, and the C3 as it aligns with the Red Lake mine trend. Like I mentioned, C4 is just an isolated conductor. We don't really know what caused that. At some point, it connects with the large-scale lower crustal conductivity anomaly, but in most cases it doesn't. And the C1, at first we thought that's the boundary. I mean, it corresponds, it links the Sydney Lake Fault zone, and probably that's the buried boundary between the Uchi and the English River terrain, but maybe that's not right. I don't know. Up until now, we had to stop after a while. So, but with that, having said that, so we pulled the seismic data, and we just massaged this a little bit, and reinterpreted it based on the combination of information from Calvert 2004 and Van der Velde in 2007. So we added our own spices, to get things going in our way, I believe. And two important features are the large-scale crustal scale fault that extends from the boundary between Winnipeg River terrain and English River terrain all the way to the suture between the North Caribou and Winnipeg River terrain at depth. We have a bunch of non-reflective zones, and the second important feature is the south deeping thrust faults that were reactivated according to Calvert during the orogenic or at the end of the orogenic event, orogenic collapse. So those are the two important features. There are other small scale features, but those are the ones that are really important at this time without wasting your time too much. So we superimpose this seismic interpretation on the empty section taken along the crooked line. It's not a straight line, but taken along the same seismic line to have the same information and compare them. Empty section is not as long as the seismic, as you can see to the south. But overall, we have a good agreement. Our C1 here corresponds to this fault, and we interpret that to be devolatilization, subduction-related devolatilization fluid that moves along the subducting plate. The C0 corresponds to the suture between the North Caribou terrain and the suture zone area. So we believe this is the source of the fluid that transported the gold from the lower cross from the source to the sink, I should say. That's a better language. And we can also define this line, like I said, as the boundary, the lower crustal boundary between this block and this block, as well as this one corresponding to the upper crustal boundary between the Winnipeg River terrain and the English River terrain. Maybe if Eric looked closely, he might be able to trace this to the top. We believe it was this boundary, but there was no sufficient evidence to support this notion. Probably we have a bunch of S-type granite here and there, but more importantly, the English River terrain was deposited after the deformation, the collision event. So the sediments it wasn't really even deposited at that time, so we can say it was transported to depth to create this feature. And the C2 and C3 are also interpreted as the fluid pathway through which this fluid that was generated here moved to the near surface. Now, so the interpretation of this region as the source of a carbon-rich and gold-bearing fluid, as well as interpreting these conductivity features as the fluid pathway, requires them to have formed before the actual main state gold mineralization. So they predate 2.712, or they were formed between 2.723 and 2.712, I should say. And also, you would notice that we have a resistive feature up here, and you might ask, why are they not really extending from this point all the way to this point? And that can be explained by a bunch of reasons, including overprinting relating to late-stage tectonic intrusions, up to the extensional tectonics that occurred at the end of the orogen there, the Kenorian orogeny. So similarly, Henson et al., they have a replica model for the Lachlan gold field in southeastern Australia. They have a large-scale, less than 20 ohm-meter conductivity anomaly. They attributed that as the source of the fluid that ran through all these faults that have been overprinted, and that was interpreted to be graphite relating to the interaction between the carbon and pyrite-rich sedimentary rock that was buried in here and devolatilized by amphibolite Fashi metamorphism. So, taken together, this cartoon shows the tectonomagmatic model for Red Lake. So, to have the fluid and devolatilization and everything, we need the heat. So the source of the heat can be attributed to either the slab break-off associated with the collision or convergence, or the delamination. Or it could be from the mantle-derived melt that interacted with the lower crust. One way or another, we got our heat from the mantle. And that set up the large-scale metamorphism that devolatilized the subducted supracrustal rocks. They're subducted along with this plate. So this is where the fluid was produced, and the devolatilization process released all the fluids and gold and everything else, the carbon that got transported along the faults to use and reuse the deformation zones for the gold deposit. Like I said reuse because we had two stages of gold deposits, the first and the last stage. Also, we could attribute the final stage to the extension that produced, there could be enough heat from the extension itself, and it remobilized the gold to have the second stage of gold. And I should mention that the main stage produced a lot more gold than the last stage, but the quality of the gold for the last stage is way better than the quality of the gold for the main stage. So now to the conductors. Yeah, I know. You would think, yeah, it's going to say graphite again, but yeah, it's graphite or sulfide or combination of both. Now, when you look at the reaction, there is hydrothermal reaction with the host rock, which might precipitate the graphite along the fluid pathway. But at the source, when there's this large-scale reaction, then there will be precipitation of carbon or sulfides. And you don't need a whole lot of graphite to have this large-scale conductivity anomaly. The most important thing is interconnectivity. Tiny pegs that are connected, it's good enough. So 0.01% of graphite is good enough for you to have less than 50 ohm meters of conductivity. So in conclusion, the tectonomagmatic model includes, for the Red Lake gold mineralization, includes the convergence, cessation of subduction, delamination, and slab breakoff. So the conductivity anomalies, or the enhanced conductivities we image here, represent the footprint of the events associated with the gold mineralization. And the heat source, like I mentioned, we need heat to have this kind of interaction, and it could be from the slab break-off or delamination, or from the interaction of mantle melt. Again, the extension, like I said earlier, the extension could also be held responsible for the late stage gold mineralization because it's capable of producing enough heat and reactivate the pathway for the journey of the mineral, of the fluid from the near surface, from the lower crust to the upper crust. However, our result, we ran a bunch of tests. Our result does not preclude mantle contribution to this gold. There could be, it's possible, but it's just that our test does not support it in any way. Also, we could have some gold minerals there in the mid to lower crust that were, introduced by previous event that just got remobilized by the devolatilized fluid. Yeah, that's also possible. However, the observations we made in our study strongly suggest that it was all from subducted supercrustal rocks. So we thank everybody there. If you find your name there or not, we thank everybody, and thank you.